I'm Daniele Lezzi from Barcelona Supercomputing Center. I'm here for a short demo about the COMPS superscalar framework that we developed at BSc. Here I represent the results of our work in projects like EUBrazil Cloud Connect and Transplant. I will give a very short presentation to go faster to the demo, even though maybe during the demo I will come back to the slides because something we have to wait for the machine to be created, etc. So just a quick outlook to COMPS. COMPS belongs to a family of programming models that we developed at BSc, and the main idea is to abstract the logic of the implementation application from the underlying infrastructure. So COMPS superscalar includes a programming model, which is a sequential programming model. The user has not to deal with any API or with any programming language. The idea is that the user has his own application already developed in a sequential way, and then there is a general purpose task-based programming model that allows the automatic parallelization of the application and the deployment and execution on underlying infrastructure. It's important to say that the same application the same code can be executed on different resources like supercomputers, Nostro in BSc, or cloud, as in our case in the demo now in EGI, or any grid infrastructure. So the aim is to reduce the complexity of developing the applications for this distributed infrastructure. And the target of application that we deal with this specific programming framework at BSc COMPS superscalar are application composed of tasks of the granularity of these tasks are programs. Okay, so we are not talking about threads or processes like in MPI, for example. We are talking about programs, okay, binaries, for example, and these tasks are executed as a workflow, and the data exchange can be files, objects, data arrays, or other primitive types. We natively support Java, which is the native language of COMPS superscalar, but we also have bindings for C, C++, and for Python, which is interesting because many scientific community, for example, life science, have many applications developed with Python. So in this picture, the idea is that there is a user code. Okay, the user, as I said, doesn't have to change the application, as just to annotate the part of the code that is supposed to be a task to be executed remotely. And then there is the runtime that intercepts the calls from the sequential code of the user and execute this task in the available nodes of an infrastructure. So the runtime builds an execution graph, resolves the dependencies, and execute in parallel, where possible, the tasks on the nodes. We always takes a lot of attention to interoperability, and we think that interoperability can be achieved above all through the adoption of standards. That's why our involvement in OGF during the years, in EGI now. Here in this schema you can see that our runtime supports different infrastructure, whereas possible we have standards like OCCI, like grid FTP, etc. So the idea is that we want to achieve interoperability, which is also the aim of the demo today. So the demo. The application that I will execute is, let's say, a stupid application, because the aim of this presentation is to show that COMPS is able to create, to execute the tasks on dynamically deployed virtual machines in federated infrastructure like the EGI Federated Cloud 1, and using multiple providers during the same execution. So I will generate an execution graph, an embarrassing parallel execution, and the virtual machines will be created on demand depending on the load of the application. So the runtime will detect an increasing load, a computational load, and will deploy accordingly the virtual machines. So the testbed is the following. We have the programming model enhancement service, which is a service that allows the deployment of both COMPS superscalar applications, but also standalone applications and services on distributed on cloud infrastructures. So we have the machines available at SESnet. We have 3 machines, already created virtual machines. The one that provides the endpoint for the enhancement service that I will access through a dashboard, a web dashboard. And then we have 2 statically created virtual machines, but I will use just one. The one that execute the COMPS superscalar application. And this has been created, of course, through OCCI. And then we will create dynamically more virtual machines as long as the execution goes on the same provider, so on SESnet. And then we will use another provider in Italy, Bari. It's interesting here to say that through the same interface, we are able to transparently deploy virtual machines on OpenNebula and OpenStack backends. This is completely transparent. The application is not statically installed in the virtual appliances, but is deployed by the runtime to the newly created virtual machines. All this software is available in EGI Marketplace. These machines, these images are available in the AppDB, in the cloud marketplace. So the software is available there. You can download and test it. I will go back to, I will start the demo. So here, the programming model enhancement service is a web service that implements the OGF base standard. So it's a web service that implements the basic execution service interspecification. So here we access it through a web interface. This dashboard allows the configuration of a user environment with the COMPS applications. Okay, so the user here can, for example, add new application. Here I have of course an already available application that I called elasticity. Here the user can also configure the storage. The storage can be FTP. In our case, we will use FTP, but we also support CDMI. Okay, and I will show you that through this interface we can also monitor the job. Just for technical details, so I will log in to the PMS node. By the way, I have to say thanks to Boris as always, because he helped me on the deployment of the machines. So here I'm logged in a machine SSNet, that is the PMS virtual machine. This is the Rocky client. Through the Rocky client, I can show you that here I have created 5 virtual machines, but these 3 are the important ones. The first one is the PMS service, and the other 2 are 2 statically created virtual machines. One will be used as master for the enhancement of the COMPS application. Okay. So let's execute the application. So here I select the elasticity application. What we do here, this application, as I said, is a really stupid one. But here what we do, we instantiate 80 independent tasks. Then we wait 2 minutes. and we generate 220 more tasks. Okay, this is to allow COMPS to force, let's say, COMPS to detect that there is an increased load, computational load, so it will be forced to create new virtual machines. Here the user can configure several parameters. This is the clock time that is needed to terminate the application if the application goes behind this value. And here the user can specify constraints on the test bed. So here we say that we need machines with 4 cores and 4 gigabytes. Here, again, for demo purpose, I will pre-create 3 virtual machines. And I say that for this run, I want to use at maximum 5 virtual machines. These constraints are translated automatically by COMPS to virtual machine templates. Okay, so COMPS is configured with the details of the templates at each provider, SESNet at INFN in Italy, and will ask to the OCCI server for the proper machine which respect these constraints. So I will submit the application. So here the application now is running. If we go to the log, you can see here the server that is now deploying the package, the application to this machine. Here you can see that there is the application started, but more than this log is more relevant to see that the resources asked during the computation. You can see here that there is the provider Prisma, so INFN, which has been asked to create 2 virtual machines. If you remember here, I specified through the dashboard that I wanted to start with 3 virtual machines at least. The PMES, as I said, contains the information about the providers. One of these information is the number or maximum number of virtual machines that I can create on each provider. For the demo, I fixed 2 virtual machines to each provider. So, as you can imagine here, a part of INFN, which is already been asked for 2 virtual machines, also SESNet now has been asked for a virtual machine, because we said I need minimum 3 virtual machines. Each provider has a limit of 2, so there will be 2 and 1. In the second run of task execution, also SESNet will have more than 1 virtual machine. Here is the monitoring of the execution of the application, of the COMPS Presca application. As you can see here, there is already available 1 virtual machine at INFN. So this is an OpenStack virtual machine. So also the second one. INFN is really quick to create virtual machines. So you can see here that we have a virtual machine created through OCCI. These are large virtual machines. Okay. So here should appear sometime also that there is the tasks that are being executed. But of course, we have to wait for the third machine to be created, because we asked for 3 virtual machines. SESNet is a bit slower at the moment on generating the resources. But if we use the client, we should see, as you can see here, this virtual machine has been created now dynamically by COMPS. We have to wait for its availability. If I can ask the endpoint for the details, we will see that the appliance is still inactive. So we have to wait. So what we like now, okay, so this is the actual load detected by COMPS. This is as I said, is an execution graph which is very stupid. We have 80 tasks that are going to be executed in parallel as long as the machines are available. So here you can see that the task started to be executed on the nodes. So we have 8 cores for each virtual machine. So we have 8 parallel tasks executed. As long as the third virtual machine will be available, we will see that we'll have 12 parallel tasks executed in a few seconds. We developed this code again for demo purposes. Of course, we have much more complex applications with much more complex workflows, which include data dependencies. So in this case, the runtime will take care of resolving the dependencies between tasks. We'll move here the third virtual machine appeared. As you can see, the IPs are different. So I wasn't lying. So it's true that we are creating, that we are executing on a multi-provider testbed. So again, in the case of more complex workflows, COMPS will take care of transferring also the files to the nodes. There are several policies to decide which is the best node where to execute a specific task, depending on the data locality. In the case of settings like the ascetic ones, BSC is part also of the ascetic project as presented by Django. We are also evolving the runtime to support energy constraints. So the task will be executed on a node that is compliant with certain energy constraints, etc. So here we can see that the tasks are being executed on these resources. Through the dashboard here, we can see that we have, at the moment, we have 80 tasks, as I said. Now the runtime is blocked to wait the completion of this task, and then we'll generate 200 more tasks, as I said. So here we can see that we are executing 52 tasks, 28 already completed out of 80. We have to improve this dashboard because here there is not the complete list of resources. Here you can see another interesting thing. Now COMPS has decided that these 3 virtual machines created at the beginning are not enough. He knows that can create more because the total, the maximum limit is 4, 2 virtual machines per provider. So here is creating another virtual machines to execute the rest of tasks. Okay. So he has 3 virtual machines, but he knows that he can do better because he has other tasks in the waiting queue. So he's asking for more resources. So the 4th virtual machine will eventually appear here. So this is to demonstrate the capabilities of COMPS, of the runtime, to profit from a federated infrastructure. In EGI, for example, we have a number of providers. The providers are supporting the virtual machine, the virtual appliance, okay, through the mechanism developed in EGI. Here we have 4 virtual machines, which is the maximum that I set in this demo. Of course, I could have created more machines here. This would have been much more faster. But we calibrated this demo to show that our machines appearing, disappearing now. Okay. Sorry. Here we can see the user has also the details of what's happening behind the scenes. This is the log of the application. Okay. here you can see that the tasks have been created. Okay. We are going also to, this other button is to support what was discussed before, described by Boris. The fact that the user can change dynamically the number of resources available during the execution of an application. So this maximum number actually can be scaled up or down during the execution, and the runtime will be notified of the new configuration. So, in the meantime, we can go back to the slides, and I can describe more details about COMPS. So, as I said, the user hasn't to deal with details of a specific programming APIs or language like MPI or OpenMP. Anyway, as I said, the user has to select the part of the application that will be treated by the COMPS runtime. And we provide now a graphical interface, which is a plugin for Eclipse, which is available through the Eclipse marketplace, that help the developers to implement COMPS superscalar application. So there is a way to annotate the main program, to annotate the interface, the generation of the configuration of the testbed where the application will be executed. It can be also described easily through the graphical interface. And above all, there is the availability of deploying from the developer interface to deploy the application on the infrastructure through the use of the enactment service. So instead of accessing the enactment service through the dashboard as I'm doing now, the user can programmatically access it through the graphical interface. So this is the what we already showed, the COMPS runtime monitoring, where the user can see the advancement of the execution of the application. There is the possibility to generate traces to analyze the performance of the application at the end of the execution. This is done through the Paraver tool, also developed at BSc. This is a really powerful set of tools that allows the user to detect imbalances in the application, to detect the time required by each part of the application, transfers, execution, access to this disk, etc. These are the more low-level details about the runtime itself. We have several components. For this, more relevant today is the fact that the resource manager is, as I showed, is able to elastically manage the resources interfacing to several cloud middlewares. Here we are using the OCCI standard, but actually in the same run, we could use OCCI and Azure or Amazon resources. So we have examples of execution of the same application on private and public resources. Okay, so it's really interesting for outbursting. And the resource manager can, as I said before, has different policies, and that now are being extended also to support energy, to decide which is the best provider, and inside the same provider, which are the best virtual machine to execute the task. The code and the packages are available through our download pages, but also if you are interested, the software is deployed in the EGI federated cloud. Thanks to Boris for doing this, for helping me do this. And but also you can download this OVA and install on your laptop. Okay, so the same virtual machine can be installed on your laptop if you want to do a test. As I said before, as we'll explain later in the next demo by Francisco, we are now using COMPS superscalar and the PMES in the Cloud Connect project on top of the Fogbone middleware that we'll use to federate the underlying infrastructure. This is a collaboration between Europe and Brazil, where people are bringing their assets, their components, to build a worldwide, let's say, federated infrastructure. We are not reinventing the wheel. We are following the EGI developments in Europe, okay? So we are also, again here, taking into account the interoperability, real interoperability with the existing infrastructure. And also the COMPS and the PMES are now used in the transplant project for supporting life science communities. We have a very similar deployment there. This is our group, led by Rosa Badia. And now, if I come back to the demo, we should have less machines here. So you can see now the application is ending. Okay, so you can see now the number of tasks is reducing. So COMPS has detected that there are no more tasks to be executed, so is switching off the virtual machines. And we have just one virtual machine on each provider. So if I cannot, I mean, this is really for us interesting to do these developments because help us to increase our interoperability. So the work in EGI, we are really proud to support EGI with our tools. COMPS is available, by the way, as a platform level tool on top of the EIS infrastructure. We are supporting new user communities that are willing to profit from the EGI federated cloud but need more high-level tools. Still, there are problems to be solved. We need a stable CDMI implementation to support CDMI endpoints. This is something, I mean, this is ongoing in EGI. There is an ongoing discussion. And something that we always talk also with Boris, we need a federated storage. We need an interoperable solution because there are solutions, of course, but we need a standardized solution to have in this kind of executions. I mean, I used multiple providers, okay, but this could be improved for more complex application if the user could have a real cloud storage in this kind of testbed. So a place where I put my data through CDMI, of course, to be interoperable, but I put the data and then I know that all the virtual machines share this storage. I don't know if EUDAT can help on this. I saw on your slide that you adopt on cloud, right? That maybe.
There is one, yes. So in that case, we might want to deploy.
So by the way, sorry, here the application is finished. All the virtual machine has been switched off. And I mean, here it's failed maybe because the clock time wasn't set properly. So maybe the application at the very end has been cut by, by the system. But it's not important, sorry.
That's right. I was just thinking out loud as usual that if we deploy a EUDAT credential within your federated cloud, which we've done before, or not EUDAT, but Contrail did it,
yeah.
And then use that to mount storage resources within the virtual machines. That might work.
So the Exceed is producing an Exceed-wide file system that Grimshaw's been working on. But I'm not sure how cloud-like it is. It's just intended to be across those resources.
Because now what we have, for example, at SESNet, this the first virtual machine that you see here actually is a virtual machine that acts as a NFS server. And the other machine are configured to attach this NFS. But this is not supportable, to be honest. I cannot take this setting and go to another provider because I have to ask them to install an NFS server, provide a public IP, etc., etc. So we have been used this setting for specific use cases, as in the OpenBio project, because we need a shared storage where to put, for example, the input data. Imagine a large data set needed this input for a computation. You cannot move to each virtual machine. You cannot create a block storage on each virtual machine and copy the data there. It could be useful to have a sort of CDMI cloud storage as we had in Venus C, but then each virtual machine could automatically attach this storage. Yeah, sorry.
I'm trying to
Just
take
going to
notes at the same
reconnect
time.
the
No, I mean there are many solutions. No,
Yeah.
the important thing is that, for example, in EGI, several things have been decided and adopted as a standard. Let's say, okay, so we agree that we have to use OCCI for the virtual machine management. So all these different developments around sync and share storage, like sort of Dropbox or whatever, should come to a to a final decision. Yeah. So just resuming, we are able to do many funny things, but there are still problems to be solved.
Okay.
Okay. Thanks.